This is problem 2 from INOI 2013. It's called sequence land. In this problem, there are n people, and each person has an ID, which is a sequence of numbers. Two people are said to be related if they have at least k common elements between their respective IDs. We have to find the size of the precedent's extended family using the IDs given to us in the input. The precedent is the first of the n sequences in the input, and the extended family of a person is anyone that's not a complete stranger to them, meaning anyone that may have a chain of connections to the person is related. For example, if my relations look something, if these are the n people, and this is the precedent, and my relations and the relations in this situation look something like this, then we would say that there are 4 people in the extended family of the precedent, even though this node and this node are not directly related to the precedent, they do have some sort of connection. Whereas these two nodes have no connection to the precedent and are complete strangers. When I think about this problem, the first thing that comes to my mind is that this is a graph problem, which requires us to tell the size of the connected component that includes the first vertex. The relationships between people can be viewed as a graph and the extended family of the precedent as the connected component. Now, we can simply break down our solution into a series of actions. First, we find all the direct relations we find the direct relations using the sequences given to us in the input. Second, we use the relations to build our adjacency list. Third, we traverse the graph that's connected to the precedent. And while doing so, we also count the number of nodes in the connected component. Let's try to use the steps I just mentioned to solve the sample input. This is n and this is k. This column right here is the number of elements in each sequence, and I've also numbered the sequences starting from 1 just so that it's easier for us to work with them. Let's try to build our adjacency list using this information. Let's compare 1 and 2. We see that there are 2 common elements, 4 and 8. So we can fill 1 and 2 in the respective adjacency lists. Next, we compare 1 and 3. We find no common elements. And we compare 1 and 4, and we find only one common element, which is less than k. So we don't consider 1 and 4. Next, we compare 2 and 3, which also has no common elements. Coming to 2 and 4, we see that there are 2 common elements, 0 and 8. So 2 and 4 are related to each other. And 3 and 4 also don't have any common elements, so they're not drated to each other. If we were to build the graph using this adjacency list, we would get, let's first draw all the vertices. Okay, so 1 is related to 2 and 2 is related to 4, and this means that there are 3 members in the. Coming to the code now for the solution, we begin by taking an n and k, after which we using loops we take in the sequences. First, we take in the number of elements in a sequence and then the sequence itself. We also sort each sequence individually so that we can match the common elements between a pair of sequences more easily and reduce the time taken to do so while forming our adjacency list. Next, we use nested loops to find the number of common elements between all possible pairs of vertices and compare them to K over here. If they match a condition, we add them to our adjacency list. And since relationships are both ways, we make an adjacency list for an undirected graph. After that, we traverse the connected component of the first vertex by calling DFS on it. Depth first search, or DFS, is the recursive function that traverses all the nodes of a graph depth-wise and visits all nodes only once. Over here, the variable for answer is keeping count of the connected component. And once the function returns, it outputs the number of members in the precedence extended family. That would be all for this problem. Thank you for watching.